B is Baku, no longer in Russia. M is Moscow. The problem is, to get, using these edges, what is the shortest path from Baku to Moscow? Using this graph. Can you spot the shortest path? What's the shortest distance? Suppose you're going by car or something. You have to follow these green lines. What's the shortest distance from B to M? Well, it's not that hard. Yeah. So the shortest distance, I'm going to write it like this, the shortest distance from one vertex to another means the sum of the lengths, the sum of the weights. I'm trying to minimize the sum of the weights of the paths, and the answer is 11. And the shortest path, if you didn't spot that, the shortest path is, to achieve the 11, we've gone from Baku to Tbilisi, how have I got the 11? 2, 3, 5, 7, yeah. So Rostov on the Don, on the River Don, to Kiev, to Moscow. That's the path that gives me 11, okay? Because I add up the weights of the edges, that's 2 plus 3 plus 2 plus 4, which is 6 plus 5, which is 11. You might be tempted to say the quickest thing is 2 plus 3 plus 7, but that's slightly, although it appears to be a shorter as the crow flies, the weight in this graph theory sense is more, because it would be 5 plus 7, which is 12, not 12. So we need a systematic way to find that answer. I mean, here the graph is sufficiently simple that you spot it, you more or less spot it in a minute or so. But if the graph is more complicated, of course, it's not easy to spot. So we need a systematic way, and that's what Dijkstra's algorithm gives us. And the one way of explaining this is to actually, for once, I'll give you a table to explain the method. So the way you do this is you can write down a table. In practice, you can label the vertices, as I did in that other graph, but I'm going to show you this time with a table. So with a table, we're going to write the vertices in alphabetical order along the top. So B, K, M, O, R, T, U. Does anyone know what O is? Yeah. U? Russian city. Ufa. Okay, so we've got those seven vertices, and we're going to start at vertex B, so that gets labelled. What I'm going to do here is I'm going to put the labels on a table rather than on the graph. The graph's messy enough. Let's put the labels on a table. So the labels, which is more complicated now because I have weights and they don't grow quite so easily, the labels are going to be put on a table. So Baku, B, is 0 because we're starting there. So obviously the shortest distance from B to B is 0. And because we haven't scanned any vertices at this point, to make it sort of systematic, we label all the other vertices with infinity because we haven't actually seen them. So at this point we can't even get to them. So there's infinite distance at this point in our consideration from B to all the other vertices. Then what we do, as I did before, is to look at the existing labels and choose the smallest one. Okay? Well, obviously the smallest one is 0. I mean, I could have skipped this step, but I'm just being systematic. So the smallest one is 0. So you highlight that, and you actually bring what you're really doing is you're bringing B out of the queue. You can think of a queue forming here, but in a different order. And then B is brought out of the queue, and now we're going to use B to scan the adjacent vertices. So what we do is we look at now, as we did before, we look at B and we look at its adjacent vertices. Well, T is adjacent to B, and that has weight 2, that edge. So it's no longer 1 because the edges have weights. B to U is 6, and we can get to R and also with 6. Okay, but we can't see the remaining vertices directly, so they stay at infinity. B is out of the picture. So these are the new labels. So we've got some new labels, 626, because we've used these edges here, here, and here to do some scanning. Now what we do is we look at you can imagine these labels have been put on the graph, the 6 to 2. I mean, I could in fact put the 6 there, the 2 there, and the 6 here, and the 2 here. And I look at the smallest number of these, but there are too many numbers, it gets confusing, but I look at the smallest number, the smallest of the vertex labels. And of course the answer is 2. The 2 is the smallest one. I better get rid of those, they're too confusing. 2 is the smallest one. So that's telling you that we're going to bring T, Tbilisi, we're going to bring that out of the queue, and we're going to use that as the next vertex to scan others. So these vertices on the left are called the permanent vertices. So here we sort of have this column, the first column here, consists of what are called the permanent vertices, for which we know the correct shortest distance. This being the first column. What I'm telling you, it's completely obvious in this case, is the shortest distance, T has been put on the left, so has B. Obviously B to B is 0. The distance from B to T is 2. I can put it as a subscript if you like. So this 2 is the correct shortest distance. On the other hand, we don't know for certain whether the correct shortest distance to R is 6. In fact, it's not. It's going to be 5, because in a moment I can get to R via T, and that gives me a shorter distance of 5. So these distances, these numbers on the right, these labels they're called on the right, are what are called temporary labels. They're not necessarily giving you the true distances. So we then use T to do our scan, and we've scanned B. We can get to Odessa from T, so that gives me a distance. Well, I've got to use the distance I've already got from T, but I can add 2 to that, so T to O gives me a 4, and then there's nothing else, and then there's T to, I can also look at R. Okay, R can still be looked at because it's not on the left-hand side, so T to R gives me a 5. So this 6 gets improved to a 5. And then we just bring down, the 2 has gone off the map here and has gone to the left, so we just bring the 6 down, that's unchanged. And I guess the infinities are unchanged as well. So having used T, the table looks like that. And again, I choose the smallest number. The smallest number is 4. So the 4 tells you to bring down O and make that a permanent vertex, and its distance, its corresponding label is 4, so that is the true shortest distance from B to O is 4. That's correct. I can't improve on this path. And then we go, I'll do the lot because it's a very small graph, and then we scan from O. So O now has this permanent label of 4, if you like, so that's the starting sort of distance. Well, I can get to K now, adding 5, so that means I can get to K, so the distance from K to B via O is going to be 9. That may not be the shortest distance, in fact it isn't. O to M I can't do, so that stays at infinity, that's gone. O to R is well, it would be 4 plus 4 is 8, so the 5 stays. Can't improve on the 5. And the O to U, I can't improve on the 6. Okay. So now I've scanned O, and the smallest distance is 5. So R, the theory tells you, it's not completely obvious, but the theory, which I'm not going to do today, tells you that the shortest distance from B to R is given by this 5. So R comes on the first column. It's confirmed shortest distance from B is 5. And then we scan R. Well, we're almost finished. R can see K, and since we got to R in 5, it can get to K in 7. So that's an improvement on 9. So I replace the 9 by the 7. I can also get to M. That would give me a 12, which is an improvement on infinity. And then I only have to worry about the U, where that would give me a 13, but that's no improvement on 6. So now the smallest label is 6. So the U comes down on the left with a distance of 6. And U to K I can't do, so the K stays as 7. U to M is not going to improve on 12, so the 12 stays the same. And there's nothing left once everything else has gone on the left. And then the 7 is the smallest number here. The 7 corresponds to K. So the only thing we have to, the only one left is M. So K is adjacent to M, and it's a distance 4. So I have to add that to the K came down with a label of 7. Forgot to say, being the permanent, the shortest distance. I can get from K to M in 4. So that gives me my 11. Which we know is the correct answer, and everything else is finished, so that gets confirmed, and then the 11 comes down, if you want to finish it off, comes down as M. So that's a systematic way, that's really the essence of Dijkstra's algorithm. So you just label, starting from a given vertex, you use that to label the other vertices. Well, the first step is trivial. Then you use adjacency, you use a breadth first search, but the order in which you order the vertices is determined by the weights, the total distance. So you always take at the front of the queue the vertex with the least distance from the starting vertex. Are there any questions on the method? I'll do another example, yes?
Would you do it for two share the same short?
You chose one. It doesn't matter. You choose one. If, of course, you take it in alphabetical order here. If 2, you take the one with the letter. If you want to instruct the computer or your brain, you just, if they're already ordered by some letters or numbers, you take the least, say. It doesn't matter. You'll get the correct result. Where are we? Well, you can get a tree by this method. You can get a tree. I won't illustrate it in this example. It's in the notes. I like to give you a slightly more sophisticated example in which I won't do a table. I'll go back to putting the labels on the graph. Now, I'm going to put the labels on the graph. So we're going to start from this vertex here. This is going to be our starting vertex, and we're going to find the shortest distance from that vertex to every other vertex. So obviously we start by, and these big circles are trying to sort of make it easy for doing the exercise. So the distance from this vertex to itself is obviously 0. Then using that vertex, I scan adjacent vertices, and I put the corresponding distance, I call it distance, it might not represent true distance, corresponding weight if you like, but distance easy to understand. I put the corresponding distances outside the circles because they haven't yet been confirmed. They will, of course, be the shortest distances, but strictly speaking, in the process, they haven't been confirmed as the shortest distances. I've now done this vertex, but I then have to look at the numbers on the page and take the smallest one, and the smallest number, or the smallest label, is 2. So that 2 gets made permanent. So I write it inside, and it becomes the true distance of this vertex from S. Having done the 2, I then use this as my current vertex, and I look at all its adjacent vertices. So this one's been done. I can go from 2 up there, that would give me 11. And here you have to check what I'm doing. I can go to here, that would give me 4, because it's 2 to there plus 2 is 4. And I can go 2 plus 4 is 6. But I don't write the numbers inside because I don't yet know they're the shortest paths. But when I look at the existing numbers outside the circles, there's an 8, 11, a 4. Obviously 4 is the smallest, so that can now come inside, and I'm certain, the theory tells me, you can try and ask yourself why it's true, that it must be the case that there's no path from here to here shorter than 2 plus 2. It's obvious if you stare at the graph, but quite why that's true is not so obvious. There's no shorter path than 2 plus 2. So the shortest distance from S to this vertex is 4. Now I'm at this vertex, and I use this to scan adjacent vertices, so the 4 plus 3 will give me a 7. This has been done. 4 plus 8 will give me a 12. 4 plus 3 will give me a 7. And that's it. Now look at the remaining numbers. What's the smallest one? It's the 6, right? Agreed? So 6 goes permanent. 6 plus 1 is 7. I've now done the 6. I really should have put ticks when I finished. I've done the 6. Now, what is the smallest number? Well, there are the 3 7s. It doesn't matter which one I start with. Let's start at the bottom. This is a 7, so I make that permanent. 7 plus 3 is 10. Well, that's an improvement on 12. So get rid of the 12 and replace it by 10. That's a key point in this relabeling. That didn't happen before with the grade graph. Okay, with the grade graph, you never had to relabel. I didn't need to put numbers outside and then inside, but that's because it was a special case in which all the weights were 1. In the general case, you have to relabel sometimes because you find shorter paths, obviously. So 7 plus 3, that gives me a better distance of 10 to here, to there. 7 plus 5, this hasn't been labelled at all, so this can go down as 12. 7 plus 3 is 10, that doesn't improve on the 7. So that's done this vertex, and I move up to this 7, so that can be made permanent. 7 plus 9 is 16, that's not bigger, that's not smaller than 8. This has been done, that's been done. 7, be careful here, this is a 6 here. 7 plus 6 is 13, but we've got a better number of 7, so that's now been done. Now I've got this 7, which can be made permanent. And I've got 7 plus 1 is 8, which is better than 12, so the 12 gets replaced by 8. And that has done this vertex. Now, what's the next smallest number? We've got 2 8s. Well, let's start with this 8. Oh, no more 7s. This 8. 8 and 5 is 13. I've done that 8, and then I've got another 8 somewhere there. So we've got an 8 plus 7, this is a 7, not the 6. 8 plus 7 is 15, that's no good, because we've already got an 11, which is smaller. 8 plus 5 is 13, but we've already got a 10, so there's nothing more to do. 10 is the next smallest number, I think. No, 9. So 10 can be made permanent, but there are no more, we can't do any better, and there's no, these are all permanent, so nothing more to do. We've got an 11 here. 11 and 4 is 15, that's no better than 13. The other two have been done. And then we've just got our 13, which becomes permanent. So that's an application of Dijkstra's algorithm that gives the shortest distances from this starting vertex to all the other vertices. The shortest distance in the sense of the least sum. When you add up the weights of the paths, it's giving the shortest. So let's give an example. So if we call this, how many vertices? I'll call this V0. How many vertices are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's call this V12. So the shortest distance from V0 to V12 is equal to 10, that's what I'm claiming. And the shortest path, there may be more than one, but a shortest path goes from V0, I have to remember how I got the 10 actually. How did I get the 10? I think it came through the 7. And the 7 came from the 6. So is it 2 plus 4 plus 5? That's 7 plus 3 is 10. Yes, so it went from V0. Well, I don't have numbers here, do I? Let's call this V1. Maybe this is V4. I don't know. V5. V12. So what we're trying to do, we're minimising, this shortest distance minimises the sum of the weights, as they're called sometimes, of the edges in the path. Is that clear? Any questions? Now, this actually does determine a tree, because what we have done is a breadth first search. It's a breadth first search with, it's called with priority, because in the queue we've actually used the weights, used the lengths to reorder to decide which vertex comes out of the queue. So it's sometimes called a breadth first search with priority. This is explained better in one of the questions on the sheet, which I'll help you do maybe tomorrow. But therefore it should give us a tree, and the tree should, I don't want to mess this up, but the tree, I mean obviously this has got lots of cycles, this graph, but there will be a tree, a spanning tree, coming from this search. And it will represent the edges we're using to get to the various vertices in the best possible way. So in particular, we need to make sure that we only put an edge when the difference of the numbers is the same as the weight of the edge. So this edge here goes in because 0 to 2. We know that we got to 10 with this path, so this must be an efficient path. So these edges all go in, and then we essentially do the same thing for all the other edges. So the 2 to the 4, that must be a good edge. The 4 to the 7, that must be a good edge. 7 to 7, we don't want to put that edge in, but that's wrong. The 4 to the 7, that's edge of weight 3, so that must be the way we got to the 7. We got from the 7 to the 8 with this edge of weight 1. What vertices am I missing? How did I get to 11? I got it from up here. How did I get to the 8? I got to it from there, and I got to the 13 from there. Is that every vertex covered? I think so. So that is, how many edges do I have? Try and count them properly this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's correct because I had 12 vertices, 11 edges. So this red stuff is, the red edges form a spanning tree. Give these red edges give the BFS tree, spanning tree. And what is the total weight of this tree? That means the sum of the weights of the edges in the tree. Okay, and we've got to add up all the edges. So 2, 4, 1, 3, 2, 3, 3, 1, 9, 5, 8. Is that 11? Okay, add those up, and the total is 7, 10, 15, 18, 19, 28, 33, 41. Okay? So the total weight is 41. So this minimum spanning tree, it's not a minimum, sorry, this spanning tree which comes out of our Dijkstra's algorithm is a spanning tree that gets us from this particular vertex to all the other vertices. In fact, it gets from any vertex to any other vertex, but not necessarily in the shortest way. It's only shortest going from here. I'm not claiming that there may be shorter ways if you give two other vertices, but from starting with this vertex, this was crucial, it's giving the tree that gives the shortest distance to all the other vertices. You can draw this more conventionally as a tree and find its height. What is the height of it would be the longest path in terms of the number of edges. Okay, so it's probably 1, 2, 3, 4. I don't think anything's longer than 4. It looks to me as if the height of this tree is 4.